All right, so here we are. Excuse me. So obviously, guys, today I am away. I'm at a meeting in St. Catharines, but don't be discouraged because you're still going to get to do lots of chemistry, lots and lots. So specifically, today we are going to work on the pH scale. So hopefully you all have this handout in front of you, and we can get started. The pH scale, as you know, is a way to measure. Oh, so far, so good. It's a way to measure an acid's strength. And this is appropriate because you've been doing titrations. So over the last couple days, hopefully you've had an opportunity to test an unknown compound of hydrochloric acid and using sodium hydroxide to figure out exactly what the concentration of that acid is. But once you know that acid's concentration, once you know how to work with the pH scale, you'll be able to know exactly how acidic that hydrochloric acid solution is. So that's the goal. So the pH scale refers to the power of hydrogen. And we're going to start by recalling that acids dissolve in water to produce H+ ions, which I'll sometimes call hydronium ions, or I may call a proton, because in the end, that's all an H+ ion is. Hydrogen just has one proton and one electron. So if it's lost its electron, all that remains is the proton. So an H+ ion is just a proton. And remember that the way that we've typically written that is that we've said that an acid dissolves like this in water to produce H+ ions and those A- ions, whatever they may be. And these would all be aqueous. So that's the general form of an acid. Now, most acids only have one H+ ion. Right? The acid that we have been using in lab these last few days is hydrochloric acid, HCl. And of course, if we look, it has just one lonely little hydrogen right here. So when it dissolves in water to become an acid, we get one H+ ion and one Cl- ion. All right, so this acidic proton here, or this acidic hydrogen rather, gets released as a lone proton, and the chlorine is taking the electron and becoming the negatively charged ion. But it's worth keeping in mind that some acids actually have more than one H+ ion. And we call these diprotic or polyprotic acids. So for example, sulfuric acid, H2SO4, has not one hydrogen, but two. All right, and next year, if you take the grade, or next semester, if you take the grade 12 chemistry, we'll talk more about how this plays out, because it's not as simple as that it always loses both of its H pluses. Sometimes it only gives up one hydrogen. But for the purpose of this course, for now, we're going to suggest that this can release two protons, or two H+ ions, and it can leave us with the sulfate ion, SO4, and that, of course, has a charge of 2-. All right, and if you look at the name, diprotic would mean that this has two protons that it can release. So this is a diprotic acid. And a polyprotic acid would have even more than two. An example of that could be phosphoric acid, H3PO4. You don't need to write that. But this would be a polyprotic acid because it would have actually three H+ ions, three protons that it can release. So with this in mind, and this shouldn't be new information, the only new thing so far is this name, monoprotic, diprotic, or polyprotic, We've always known that an acid is a compound that dissolves in water and releases an H plus ion. What we want to introduce today is that calculating pH can be done based on calculating the concentration of those H pluses. We'll talk about how that works. But the strength of an acid depends on the concentration of these H plus ions in solution. So a solution with lots of H plus ions is acidic, while a solution with very few H plus ions is basic, is alkali, is not acidic. The pH scale is a way of measuring how acidic or basic solution is. And remember that each step represents a 10-fold increase in acidity. So if you remember, neutral water that's not an acid at all has a pH of 7. And an acid could have a pH of 6, or 5, or 4, or 3, 2, 1, and even as low as 0. All right, and in each of these steps, this would be 10 times more acidic, because each step on the pH scale represents 10 times. And so if we went from 7 to 6, 6 is 10 times more acidic than 7. All right, if we went from 7 to 5, that would in fact be 100 times more acidic. Because recall that each step is 10 times. So the first step is 10, and then the second step is 10 times that, and 10 times 10 is 100. And so if we were to go 3 steps, we could maybe see that from 7 to 4 would be 1,000 times more acidic. And this doesn't need to just go from 7, of course. I could start anywhere I liked. I could say that an acid with a pH of 1 is 10 times more acidic than an acid with a pH of 2. Well, an acid with a pH of 0 would be 100 times more acidic. Now again, you should have done all of this in grade 10, and I'm sure you did. What we want to talk about today is why. Why does this scale work, and how does this scale work? Why is it that an acid with a pH of 4 is 1,000 times more acidic than an acid with a pH of 7? And why is it that an acid with a pH of 0 is 100 times more acidic than an acid with a pH of 2? What do these numbers mean? Because they don't come from nowhere. So what we want to look at is some possible solutions. So I have here a whole bunch of different hydrochloric acid solutions. The first one is 1 molar, then 0.1, 0.01, and so on and so forth. Actually, I've skipped one, but that's okay. Oh, silly Joe, but that's okay. So this one here, if we were to put in scientific notation, it would be 1.0 times 10 to the exponent 0, because it's not times 10 at all. It's just 1.0. So that would be 1.0 times 10 to the 0. This would be here 1.0 times 10 to the negative 1, because I would have to move the decimal over one place. I accidentally skipped one here, but that's okay. This one here, I would have to move the decimal over 3 places. So this would be 1.0 times 10 to the negative 3. This one would be 1.0 times 10 to the negative 4. This one times 10 to the negative 5. This one times 10 to the negative 6. And this one times 10 to the negative 7. So all these different concentrations of HCl can be put in scientific notation. And what I want to make clear is if we go back and look at HCl, we saw that 1 HCl releases a single H+. So for every mole of HCl, we would end up with 1 mole of H+ ions. It's a 1-to-1 ratio, which means that if we had 1.0 times 10 to the 0 moles of HCl, then we have 1.0 times 10 to the 0 moles of H+. So these numbers should all be exactly the same. All right, and I want to focus in, I want to zero in on these exponents. So if you look, when we put this in scientific notation, the exponents do something tricky, which if I took each of these solutions, if I took a 1 molar HCl solution and I tested the pH, if I used a pH meter, it would tell me, or a pH paper, it would tell me that it has a pH of 0. If I took this 1.0 times 10 to the negative 1 molar HCl solution, which has 1.0 times 10 to the negative 1 moles of H+ ions, it would read as having a pH of 1. And if I took this 1.0 times 10 to the negative 3, this 0.001 molar HCl, it would actually read as having a pH of 3. And this one, 0.00001, which is 1.0 times 10 to the negative 4, it would actually read as having a pH of positive 4. This one would have a reading of 5. This one would have a reading of 6. This one would have a reading of 7. All of which is to say, as we get less H+ ions, as we have fewer H+ ions in the water, the pH goes up. So a pH of 0 actually represents a lot of H+ ions because that's 1.0 times 10 to the 0. But as we get less, as we have just 0.1, that's 1.0 times 10 to the negative 1, that's a pH of 1. And as we go really small, as we have decimal 0.0000001 molar, as we have this really, really dilute solution, that's 1.0 times 10 to the negative 7. If we tested that with pH paper, it would actually test just neutral. It would come out with a pH of 7. So the lower the concentration of H+ ions, the higher the pH goes. And the number matches perfectly with this exponent. It's just been switched. And that's because we measure pH by taking this exponent and just switching the sign and multiplying it by -1. Now, this works really nicely for all of these ones that go cleanly into scientific notation. But we can actually do this calculation for anything using something called a logarithm. See, a logarithm takes any number and gives you the exponent. All right, and you don't have to write this down, but I'll prove it to you. If you take the log of 10 to the exponent 3 on your calculator, see what it gives you. All right, and you may never have used the log button before, but that's fine. Find it on your calculator and plug it in, just like I'm going to here. I'm going to say log 10 to the exponent 3, and it will tell me, oh, isn't that funny? This is going to, oh, never mind, we'll do it this way. There we go. So on this calculator, you can see if I take the log of 10 to the exponent 3, it gives me the number 3. And that's because what logarithm really means is what exponent do we have to put 10 to get this. Now, of course, this is really obvious because the exponent we've put 10 to is 3, and it gives us 3. But try taking the log of the number 100 on your calculator. And again, I'll come over here. And say log 100. And it will tell me that the answer is 2. And again, the reason that works is if we take 10 to the exponent 2, it gives us 100. But it doesn't have to be a nice round number like that. I could take the log of the number 37. Now, there's no nice clean exponent that I can put 10 to, right? 10 to the exponent 1 is 10. 10 to the exponent 2 is 100. So 37 doesn't work nicely. But your calculator will still tell you exactly what exponent we have to put it to. So I can say log of 37, press equals, and it will tell me that I have to put 10 to the exponent 1.568. And we can test that. If I do 10 to the exponent 1.568, it gives me 37. All right, 36.98 is basically 37. So a logarithm tells you this exponent. And remember, that's great because all we have to do to find the pH is find the exponent and then switch its sign. So the formula for pH is pH equals the negative log of the concentration, of H plus ions. Because H plus ions are what makes an acid an acid. So here we have an example. We have an HCl solution. And remember that HCl breaks down in water to give us those protons, those H plus ions, and the Cl minus ions. And so if we have 2.43, or 2.34 rather, molar HCl, we can remember that for every mole of HCl, which we want to cancel, we get an H plus ion. And so we'll end up knowing that we have 2.34 moles of HCl per liter. This solution is of H plus ions. We can know that if there's 2.34 molar HCl, then each mole of that much give us 1 H plus, so we have 2.34 molar H plus ions. Every HCl, 1 H plus. So what would the pH of this solution be then? Well, the pH would just be the negative log of 2.34 times 10 to the negative 4. Sorry, I missed that times 10 to the negative 4 all throughout. So I'm just going to come back and change this. 2.34 10 to the negative 4 moles of HCl per liter. And we're just going to say again that we get 1 mole of H plus ions for every mole of HCl. And that equals 2.34 times 10 to the negative 4 moles of H plus per liter. So once we know that we're going to have just 1-to-1, you don't need to show this calculation every time. I'm showing it here just to prove a point. But because HCl is monoprotic, because HCl just gives us 1 H plus, whatever the concentration of the acid is, that's what the concentration of the H plus ions will be. And so now it's just a matter of doing this calculation right in the calculator. And so we would go back to our scientific calculator, and we would say we want the negative log of 2.34 times 10 to the negative 4. And it'll tell us specifically that the answer to that is 3.63. And that is the pH of this solution. And note that pH doesn't have any unit. It's not 3.63 molar, or it's not 3.63 moles of H plus or anything like that. It's just a number, all right? Because it's just the exponent on that. Just like here, this is 1.0 times 10 to the 0 molar, but the pH is just 0, because it's just the exponent we're looking at with the sign flipped. All right, and to do one more example, we can imagine another situation where here we have H2SO4. Remember we said that H2SO4 isn't monoprotic. It doesn't have one H plus, it has 2. So it would actually yield us 2 H plus ions and then a sulfate ion. Which means that if the concentration of H2SO4 is 3.45 times 10 to the negative 2 molar, then the concentration of H plus is going to have to be 2 times that. Right? It's going to have to be 2 times that because we get 2 H pluses for every H2SO4. So it's going to be 2 times 3.45 times 10 to the negative 2 molar. And that will end up being 6.90 times 10 to the negative 2 molar. And that's the concentration of H plus. Once we know the concentration of H plus, all we have to do to find the pH is take the negative log of the concentration of H plus. And so in this case, pH equals the negative log of 6.90 times 10 to the negative 2. And note that because this is times 10 to the negative 2, the answer is going to be around 2. It'll be between 1 and 2. So again, we would just take the negative log of 6.90 to the exponent negative 2, and we get 1.16. And that means the pH of this solution is 1.16. So I hope that helps shed a little bit of light on how you find the pH of a solution if you know the concentration of the acid. For all of the titrations we do, as soon as you know the concentration of the acid, you can just take the negative log to get the pH. Because we worked all with HCl, which just gives you 1 H plus for every acid molecule. But even if it is H2SO4 or H3PO4, something like that, the calculation's not that much more difficult at this level. So I hope that helps. There'll be a few homework questions assigned, which I'll put up on OneNote so that you can practice finding the pH. And I hope you all have a wonderful weekend, and I'll see you Monday when we'll be reviewing for our test. And then the test date should be Tuesday unless something changes. Have a wonderful weekend. Bye.